Welcome back. In this video, we are going to talk about how chemists use equations to represent the transformations of matter. It's not an equation that you think of in math. Let me show you how this works. We will look at how to read these equations, what the different symbols mean, and the golden rule of chemistry that mass is always conserved during a chemical reaction. So that's what's equal in an equation, the mass on the left and the mass on the right. But we have a very simple way of figuring that out, as I'll show you in a bit. Here's the basics anatomy of a chemical equation. When we write a chemical equation, we list our starting materials, the reactants on the left. The arrow indicates the direction of the change, literally meaning reacts to form. And on the right side of that arrow, we list our products, which are the substances created by the chemical reaction. We also use different symbols for the physical states to be very precise in our chemical reaction. I think we're most familiar with S for solid, L for liquid, and G for gas. And we're going to start encountering AQ for aqueous, which means the substance is a solution dissolved in water, just like this Windex glass cleaner up here on the slide. You will oftentimes see a small triangle written on top of the reaction arrow. This is actually a throwback to ancient alchemy, where the triangle was the symbol for fire. In modern chemistry, it tells us that the reactants must be heated, perhaps with a Bunsen burner or a match, for the reaction to occur. So this chemical reaction, it's a conglomeration of things. We now know what sodium nitrate and nitrate are, and oxygen, the names of those chemicals. And there's a little triangle above the arrow, meaning that you've got to heat this guy up a bit in order for this chemical reaction to occur. So pay attention to that little triangle. That means heat. Now, the most fundamental concept in balancing equations is the conservation of mass. If you start with 100 grams of material in a kettle, you must end with 100 grams. While the atoms might rearrange themselves into new molecules, the total number of types of atoms must remain the same from start to finish. We don't need to weigh anything. We just need to count and verify we have the same number of each atom on each side of the equation. If we look at this colorful figure here on this slide, we can see that, well, we have one gray carbon on each side, so it didn't disappear or get created. And we have two red oxygens on the left and two red oxygens on the right. So we have the same number and type of atoms on each side of the chemical equation. So we say the equation is balanced. Here's an overview of and summary of all that we've talked about. Again, we have reactants on the left side of the arrow. Those are your starting materials. And on the right side of the arrow, you have products. Those are the things you're forming in a chemical reaction. It's very important to notice the difference between subscripts and coefficients. The subscripts define the chemical, like the 2 in O2 tells us the formula for oxygen, and the 2 in H2O tells us that's the formula of water. Water is H2O. Those are important, but we need to focus on coefficients from here on out. Coefficients are the larger numbers in front of the chemicals, and they tell us the number of molecules involved in the chemical transformation. We will learn a lot more about that in the next video.